All right, guys, I want to talk about basic citation. Now, what basic citation is? Well, in the last class, well, not the last class, the class before last class, and the one before that, we were talking about force vibration. Right? What force vibration was? Well, the same system we had from before, a spring mass or a spring mass damper. Right? At the beginning of the semester, first few weeks, what we were doing is that we were giving that system some initial condition, some initial displacement or initial velocity. Now, what we did when we started talking about force vibration, as you remember, I said there are different types of force vibrations, there are different type of excitations in a system under force vibration, and we mainly focused, or we were focused on harmonic excitation, and that would be the main type of excitation we're going to talk about in this course. At some point, I'll talk about non-harmonic excitation a little bit, but all in all, the main type of excitation we're going to talk about is harmonic excitation. So in a system under force vibration, what happens is that we have some kind of input. We have some kind of input force in the form of a harmonic force, like sine or cosine, and that force is constantly is being applied to our system, right? As opposed to a free vibration, as they call it, that when we were just giving a system some initial displacement and velocity, right, and let it go and let it oscillate. Now we are constantly applying a force, right, to our system. And that's why it's called force vibration, as opposed to what we had at the beginning, which was free vibration. Now, there are, again, we talked about force vibration. We looked into how can we find this system response under force vibration, whether the system has a damper or not, right? It's just a spring mass, or it's a spring mass damper, the way it reacts or responds to the input, which is a harmonic force, changes, right? When I talked about beating phenomenon, talked about resonance, we looked at the transient response and a steady state response, which together form the system response for a spring mass damper under force vibration. Right? We said the transient response would be the initial response of the system to the force, because the system is going to have some initial velocity and displacement, right? You still, even though you're applying some force, your system still is going to have some kind of either fixed somewhere at the beginning when the force is uh, starting to apply, or when we start applying the force, it might have some initial velocity and displacement. They can be zero, they can be some specific value. So we still have those. And those, along with those, actually contribute to transient response. Transient response was the part of the response we said it was the uh, answer to the homogeneous part of a differential equation. And we had a steady state response, which was the particular solution to our differential equation. And we said the steady state response is the one that we are mainly interested in most cases, because that's how system reacts or responds to the input in the long term. Transient response happens at the very beginning of the motion. So if you have something that's been working or is going to work for hours, days, weeks, you might not be that much, you might not be very interested in knowing how does it react to some initial condition for the first few seconds. It's always good to check in some specific applications. You might have some transient response that gives the system huge or very large amplitude. So in terms of safety, when you're designing the system, it's better to check. But all in all, when it comes to force vibration, you will see most of the time, as you saw in the previous, the class before previous class, we're mainly focused on a steady state response. And the story continues. Even here, when we talk about basic excitation, we are mainly focused on a steady state response. All right, so what is a basic excitation? When we had our force vibration, remember what happens was that we were applying a force, harmonic force, to the mass. And the spring or a spring damper combination, they were fixed to some support. We had them fixed. If it was vertical, we had them fixed in some ceiling, If it was horizontal, we had them fixed at some support. It's a good example. I have my small cart here. Hopefully you can see that. There's a spring attaching this cart to this side of support. Right? Let's call this support. Right? Force vibration would be me moving this back and forth. Right? Let's say in a harmonic fashion. I'm doing this. Right now, this system is attached to this support, this spring. It has some damping in it, but I don't have a damper, so this can be just a spring mass system. But the idea of force vibration is I'm applying a force to just this mass, right, going back and forth, and the spring is fixed. Now, base excitation, as opposed to force vibration, well, it's not as opposed. It's you will see that we are going to use what we found for force vibration to solve the differential equation for the base excitation. Right? So if this is a spring with two masses, well, I attach the second mass to make it heavy enough so the spring is stretched. Force vibration would be me holding this side and then moving this mass, right, back and forth. Now, what would the base excitation would be? The base excitation. Well, base excitation would be I don't touch this mass and spring. I start moving the base where the spring is attached. Right? Because I move this, you will see the mass is moving, but the mass is not moving exactly with in the same way that I'm moving the base, right? Because the spring is attached here. So with a small motion, right, depending on what is the frequency of the excitation, input excitation at the base now. Right? If I move it a little bit, if I move it slowly, right, there is a very good chance that the mass is moving almost with the same profile as my hand, which in this case is applying an excitation to the base. But if I move it fast, you will see that the mass is moving a lot while my hand, which is the input excitation, is not moving that much. So the way they interact, right, is different from just the force vibration, which this one was fixed and this is just the forces applied to this mass. I hope you see the difference. Now mathematically, right, when we talk about base excitation, right, let me just put it here. So this is base excitation. So what we have is we have a, let me draw it here. We have a mass, yeah, some spring and damper. Let's not fix it. Attached to some base. Now the base is moving. As I said, instead of moving mass, the base is moving. And we want to know if the base moves in a particular way, which obviously is going to be a harmonic way, how does this mass move? If we move the base, depending on what is the frequency of this motion at the base and how fast we move it or how much is the amplitude of this motion at the base, how does this mass respond? So the way the mass responds, or I'm going to call the motion of this mass xt, and I'm going to call the motion of this base yt. Now, keep in mind that in base excitation, as opposed to force vibration, or again, not as opposed to, but different from force vibration, I'm not inputting a force. Remember I said at the beginning when we talk about force vibration, we said this can be, the force vibration can be an imposed force or can be an imposed displacement. So in a base excitation, in this situation, I'm applying a displacement. So it's an imposed displacement. I'll call displacement y sine omega t. I remember we had f naught cosine omega t. Now in this case, I'll just choose sine as a harmonic input. And I'll call it omega omega b, meaning that the omega of the base, the frequency of the base. Right? Now I want to study this system. So hopefully that makes sense what the base excitation is, and how does that differ from, or how it is different from force vibration. But you will see that we're going to use what we learned from force vibration. So similar to what I do always, I start from free body diagram, and I look at the acceleration components, and I start forming the equation of motion. Then from there, we try to solve the equation of motion. So if you look at the free body diagram for this system, let me draw it here. So this, let's say, is the mass, and this is the mass again. These two are equal. Now, this is M, and this is. Now, Y is moved, or the base is moved upward or downward. In my example with the spring mass, I was moving it downward mainly, but it's harmonic, so it goes up and down. In this specific, in this instance, let's say it is moved up, right? And the X is standing, or the mass is there at the static equilibrium at the beginning of the motion. So when I go up, the spring and damper, both of them are going to apply force to the mass, right? Pushing it upward in this example, pushing it upward. Now, because they're pushing it upward, obviously the forces I have to put on the mass, right? Newton's third law should be in the opposite direction. So the forces I put on this mass, one is downward here, and the other one downward there. One is caused by the spring, and the other one is caused by damper. What are the magnitudes? Well, K, well, obviously should be multiplied by the amount the spring is stretched. How much the spring is stretched? If I push this up, Y amount, and assume that Y is greater than X, right? It's a very reasonable assumption to make Y is greater than X. So how much the spring is stretched? Compressed in this case. Or you can go either way. You can say X is greater than Y. It depends on how what moment you are looking at. Right? It can be a small motion in the base, and the X moves a lot. So if you look at that point, let's say X is greater than Y.
Would be X minus Y.
Would be X minus Y, right? Great. I don't know who was that, but thank you. Would be X minus Y. That's how much the spring is compressed. Now to damper, remember damper deals with velocity. So instead of X minus Y, we're going to have X dot minus Y dot. These are the forces applied to the mass. And since we're starting from the equilibrium position, we ignore the effect of mass. Because if we ignore that, then whatever you're getting vertical is going to be the same as whatever you're getting horizontal when there is no effect of mass. And on the other side, this one, the acceleration would be mx double dot. Right? There's nothing new there. Because m is still moving x amount. X and y are absolute positions or displacements, so they are not relative. Now looking at these two, I can write the equation, right? Summation of forces is equal to ma. Now if I take, let's say, upward positive, what I'm going to get would be mx double dot plus c x dot minus y dot plus k x minus y is equal to 0. All right. Now we have this equation of motion. It has both x and y in it. And keep in mind that x, y, let me put it here, yt is y sine omega b t. Omega b being the frequency of the base oscillation. let me just put it here, make sure everyone knows. Omega b is the frequency of base motion. All right, if yt is this, I can calculate y dot t. Right? Derivative with respect to time would be y omega b cosine omega bt. So I'll replace this y and yt and move things around in this equation. Right? I'll get mx double dot plus cx dot plus kx is equal to, I'll take c y dot and ky to the other side, and I replace y with y sine omega bt and y dot with yb cosine omega bt. Right? So this becomes c y omega b cosine omega bt plus ky goes to the other side is positive, and I replace y, becomes ky sine omega bt. All right. You see, you might start seeing where am I going with this. I'm trying to make it more similar to what we had for force vibration. So I'm going to divide both sides by m. Remember, that's what we were doing when we were dealing with force vibration. So if I divide these by m, this is divided by m, this is divided by m, this one is divided by m, this side is by m, and this side by m. Oh, the first one is going to be x double dot plus c over m. We saw it when we were dealing with the force vibration of a spring mass damper. We said c over m can be rewritten as 2 zeta omega n, 2 zeta omega n. We said if you just use the definition, you can go backward. If you replace zeta and omega n, you can get c over m. X dot plus k over m, which omega n squared x is equal to. On the right side, again, we have c over m. Right? So it's 2 zeta omega n. Now have that omega b there and y, omega b, and then y cosine omega bt plus k over m is omega n squared, right? That would be omega n squared y sine omega bt. Pretty long equation, huh? So this becomes my equation of motion. Now, what do I do with this pretty long, seemingly pretty complicated differential equation? It's a second order differential equation and it's non-homogeneous. I have some parameters on the right side. And the parameters are, there is not just one parameter, there are two parameters that both of them are functions of time. Now, if you look at this is actually very similar to what we had for force vibration, but instead of one input, now we have two inputs. On the left side, we have x double dot plus 2 zeta omega n x dot plus omega n squared x, which is what we had on the left side for force vibration of a spring mass damper. On the right side, we have something cosine omega bt plus something sine omega bt, two harmonic inputs. And they are just summed up. Since this is a linear system, I can actually say that the response or the solution to this differential equation is the solution to two differential equations that each one has just one of these input excitations as the right side. So what I'm trying to say is that in this case, I can say this one, well, let's put it this way. Solution to this DOE, DE, differential equation, which is non-homogeneous differential equation second order, is x, well, let me write it this way, is a superposition, maybe I should have written in front of, sorry, not doing a good job in space management. So solution to this differential equation is a superposition of the solutions to the two following differential equations. What are they? Well, let me just, I can fit them here. The first one would be x double dot plus 2 zeta omega n x dot plus omega n squared x is equal to 2 zeta omega n omega b y cosine omega bt. And the second one would be x double dot plus 2 zeta omega n x dot plus omega n squared x is equal to whatever we had as the second one, omega n squared y sine omega b t. I can write a little better. Omega n squared y sine omega b t. So if you look at each of them, they are very similar to what we had as when we were dealing with the force vibration, right? Like the second one has sine as the input. But remember what we had when we were dealing with force vibration of the system. We had this left side plus something from some kind of harmonic function as the input. If I, let me put a reminder here. Remember, I can. For the force vibration, for the forced vibrations of a spring mass damper, remember what we had, right? We had this equation of motion, x double dot plus 2 zeta omega n x dot plus omega n squared x is equal to f naught cosine omega t. Remember, omega there was the excitation frequency. And for that, we said, well, the response to this, and keep in mind, we're only interested in particular part of the response solution, which is associated with the steady state response. We don't care about the transient response. So x was f naught over, if I remember correctly, square root of omega squared minus omega n squared plus 2 zeta omega n squared. That one was x. And theta was tan inverse, right? Whatever was the second element, 2 zeta omega n omega divided by omega n squared minus omega squared. This one was force vibration. We had this from before, right? Just a reminder. So if we follow this, if you look at the equation we have, look at this equation here, this equation, and go back. Let's go back to the first equation there. I'm going to number them as 1 and 2. Look at the first equation. If you consider this as f naught, well, it's the same, right? X double dot plus 2 zeta omega n x dot plus omega n squared x is equal to f naught, which is a combination of these coefficients, cosine omega bt. It's the same. So all I need to do is to replace, if I want to find the response to the first equation, I just need to replace f naught with whatever is the coefficient of cosine omega t. So for the first equation, for 1, I can find the response. I call this XP, particular part of the response. Remember, we had a transient response, and it's the part that was the solution to the homogeneous part, but that's not what we're interested in. It's a transient response. It goes away after the initial motion. I call this 1. So F naught, I'm going to replace F naught in this X that I got at the top with 2 zeta omega and omega by 2. I have to add this here too. And remember that the general form of the response for a spring mass damper was XPT, and that was the particular part of the solution, or steady state solution, was some kind of, it was X cosine omega t minus theta. Hopefully you remember this, or if you don't, it looks familiar to you from the class before last class. This one was the steady state solution.
So for that equation under remember, x equals f0 over, shouldn't the denominator under the radical be omega n squared minus omega squared? I'm sorry.
That's true. I have to flip them. By the end, it doesn't matter that much. It doesn't matter that much because it's squared. Oh, sorry, you're breaking up. But I heard the first part of the comment, which is very correct. I have to flip them. All right. Thank you. All right. So steady state solution from before, we had it as x cosine omega t minus theta, and x and theta being these variables I defined. So this is from force vibration for spring mass damper. Now in this case, as I said, I just replace F naught with 2 zeta omega and omega by. So that's all I'm going to do. So 2, it's going to be 2 zeta omega and omega y over square root of omega n squared. Now in this case, excitation, I said let's call it omega b, right? The input excitation for the base, I said sine omega bt. So let's call this omega b. Omega b squared plus 2 zeta omega n omega b squared. And that would be multiplied by cosine omega b now, t minus theta 1. I'll call it theta 1 so it's not mixed with the other theta. And theta 1 would be tan inverse, the same thing. Right? Theta 1 doesn't change because it had nothing to do with x. It was related to my harmonic input. Yes, the harmonic input changed a little bit, but for the second equation, not here. For the first one, it's still cosine. So for theta, I'm not going to change anything. To zeta, the only thing will change is that omega would be replaced with omega b, because that's the excitation frequency. Omega n squared minus omega b squared. There we go. Now this is the particular solution to equation 1. Let me just put it this for 1. The same story for the second equation. If I go to the next page for equation 2, if you go back to what we had in equation 2, I just need to call this F naught. The rest is the same. Yes, you have sine omega t instead of cosine omega t when we had for spring mass damper, but both of them are harmonic functions. The only changes you will see is in theta. The phase changes a little different. But in this case, they're the same. So as long as we have an input harmonic function, we are good. Doesn't matter if it's sine or cosine. Remember, we chose cosine as the excitation, but by the end of the day, as long as the harmonic, the input excitation is a harmonic function, whatever we found is the same. So xp2 would be, in this case, I'm taking x f naught as omega n squared y. So that would be, I'm going to go to here, omega n squared y, right, divided by square root of omega n squared minus omega b squared plus 2 zeta omega n omega b squared. And now I'm writing the response as sine, right? Because the input is sine. Previously, here, the input was cosine from before we used, so the output would be in the form of cosine. Now, because the harmonic input in this case is sine instead of cosine, I'm also writing the general form of the solution in the form of sine. Remember, we solved this for cosine, but when you have a sine as an input excitation, your response also becomes in the form of a sine function. So sine omega bt minus theta 1. Once I change that cosine to sine, now theta, the phase angle would be the same. If I had cosine, I had to add 90 degrees, add or subtract 90 degrees to my phase angle, but I just changed sine to cosine. Right. So this would be the particular solution for the equation, for equation 2. And as I said, for based on superposition, so the solution, or let me put it this way, so the particular solution, which is related to steady state response, to equation of motion that we got, that long equation, so that we didn't actually have to solve it. We broke it down because this is linear. We could use the superposition rule that says the solution of that long differential equation is basically a combination of the solution of these those two differential equations. So the particular solution to equation of motion becomes xpt, particular solution to first one, plus the particular solution to second one. Okay. All right. Now we have to simplify this. I'm not going to go into details. You're probably already bored with what I'm doing here. What happens is that if we do this, if we combine xp1, xpt1, and xpt2, and if I simplify it a little, rewrite, use trigonometry and rewrite parts of the equation, I'll get this general form of the solution. Right? Again, steady state part of the solution. That will be, I should have to take a look at this. That will be y omega n square root of omega n squared plus 2 zeta omega b squared divided by omega n squared minus omega b squared plus 2 zeta omega n omega b squared. And here we'll get cosine omega b t minus, I can do better, omega bt minus theta 1 minus theta 2. And theta 1 is the same as before, and theta 2 will be tan inverse omega n divided by 2 zeta omega b. So this is the, let's change this. This is the particular solution or steady state solution, steady state response, vibrational language, steady state response for the base excitation. base excitation. Remember, the base excitation, the excitation we had was a harmonic excitation, so it's specifically for that. And theta 1 and theta 2, this is theta 1 here, this is theta 2 here, sorry. And theta 1 is defined right there. All right. Again, long equation. We don't like long equations. We derive them mathematically because we can based on what we've learned in the math from before. This tells me that if I know the natural frequency of the system, which all I need to know for that is the stiffness and mass, and I know the excitation frequency, remember the base motion, omega b, I can find the damping ratio, meaning that I need to know mass, stiffness, and damping of the system. Then I can find the system response, steady state response for the system, which means the long-term response. And y, remember, this y is just an amplitude, right? This is just a number. Very similar to that f naught when we had for force vibration. This y is pretty much just a constant, right? Some yt is, let's say, 5 centimeters times sine omega, some frequency times t. So it's constant. So I can find the system response, the steady state response. Now let's see where we want to go from there. Now I already know that, well, the general form of the response, or I can say the general form of the response, xp, is x cosine omega bt minus theta. It's a particular solution of a force vibration. And x being the, this is different from the other x, so you can call it x prime, I guess. X being the magnitude, oh, I'm going to keep it as x, because that's what I want to talk about. And x being the magnitude of the particular solution, or the magnitude of the motion of the mass. Right? We are inputting some, we are imposing some displacement in a harmonic form, and we are getting some output. Right? Again, don't get lost in the math. Remember what physical system we were talking about. This is the system. I'm inputting some base, and I'm getting some displacement in this mass. Right? Depending on how slow I go, right, or how fast I go, the way this reacts is different. That x, uppercase x, is the amplitude or the magnitude for this motion. Right? X times some harmonic. You can think about it as the maximum displacement of this mass for any given input frequency of this system, or input to this system. That's the x. Y is the magnitude of the input. Right? This is big y, this is a small y, but with different frequencies. Right? So y is the magnitude of the input excitation. X is the magnitude of the output, the motion of the x. If you think about x, y, t as input and xt as output. All right. So what I'm interested in long equations, not easy to interpret, not easy to lock into. What I'm interested in, I want to know when I change this amplitude and frequency, when I change the amplitude and frequency of the input, how does this one change? How does the motion of this mass change? That's what I want to know. Think about a very good example is the video I shared, I think a couple of weeks ago, when it was showing how they were designing the shockers, like shock absorbers for a chassis of a car. If you think about that spring and damper system as something that was connecting, in that case that was compressed, the spring was under compression. The spring and a damper next to it connecting the road or the wheels or the tires to the chassis, right, to the structure of the body of the car. In that case, the input would be the road, right? There is a bump, so that would be the input. Let's say we have a couple of bumps, and the tire goes up and down. And the output, your x, would be the motion in your car's structure or chassis. So you want to know, how does this body or structure of the car move when this input changes, right? Depending on what kind of road you are driving, or it's bumpy, or how the bumps change, how does this car body change? So in that case, you're trying to minimize the motion of x for a given y. So what helps us a lot in design is to actually rewrite this equation as the ratio between x and y. Right? How much does x change for a given y? And I'll do it for you here. I'll just give you the final value. So to find how x changes for, oh, let's put it this way, how x t, I'll just put this x changes for given y, for given y's, I guess. We defined transmissibility, displacement transmissibility. I represent that with TD as x over y, and you can find that if you replace in this equation, replace x as replace xp as x cosine omega bt minus theta, and the other side you just get cosine omega bt and theta 1 and theta 2 as just one phase. Maybe I should have used a different notation instead of theta, maybe some phi. But you can find x over y. Right? If you take 1 omega, I'll leave it to you. If you take factor out 1 omega, take this omega n inside, take this inside this square root, radical, and then factor out omega n squared, one from the top, one from the bottom. Actually, you will get the equation that I'll write here. This will be 1 plus 2 zeta r squared over 1 minus r squared squared plus 2 zeta r squared. Double check. Yes. With r being omega b over omega n. Remember, r was a ratio, frequency ratio. And this is displacement transmissibility. Displacement transmissibility. Now, what does this tell me? It tells me how motion is transmitted, as the name says, from the base to the mass. For a given y, how much x changes? So how much this y is transmitted to x, or how much the motion of the base is transmitted to the mass. Now we have something more, it's easier to look at. So what I do, as what I always do, let's plot this and see actually how those things change. I already plotted that for different given values of, let me move it here. So this would be frequency ratio. Looking to a better frequency ratio. Ratio R being omega b over omega n. And this axis would be TD, displacement transmissibility, which is, I'll take just the magnitude, x over y. See what happens. A couple of things that you can observe in this, right? If I, let's say, let's just start at the beginning here. When the frequency of the excitation, omega b, is 0. Right? R is 0, meaning that omega b is 0. Natural frequency cannot be 0. The transmissibility is 1. What does that mean? It means if I do not oscillate, right? If I just move downward like this, or I just move upward like this, the mass and the base, they move together. The ratio between them is 1. What else? If you think about an undamped system, if you see here when the damping is decreasing, this is the smallest damping I plotted here. It's 0.1. Maybe I should use a different color. It's not similar to the colors in this figure, which is going to be hard to find. Let's just go with this. This here, right? This is this plot, this line. Now imagine that this damping is 0. This is R equal to 1. What is R equal to 1? What happens at R equals to 1? We have resonance, right? Frequency of excitation becomes equal to the frequency of the natural frequency. So if there is no damping, TD or transmissibility goes to infinity. In reality, we always have some damping. But when R is equal to 1 for an undamped system, if zeta was equal to 1, we would have seen something like this. It goes all the way to some huge amplitude. It goes all the way up. Another thing that to keep in mind. So the same story we had for a force vibration. If you have an excitation that its excitation frequency is equal to natural frequency, your system starts oscillating hugely, and it probably wrecks, depending on what type of system you're dealing with. The video I shared about the concept of resonance, I'll go over an example in next class, that you will see it actually is a base excitation, not a force vibration. Well, for base excitation is a type of force vibration, but that specifically that video is a base excitation. Another thing, if you look at this, the very interesting observation you will see that actually is very important. This point here, let me find again the color that is, why not? This one. This point here, supposed to be vertical, is the square root of 2. This value on the x-axis. R is equal to the square root of 2. Now, see what happens at this point first. So at R equals to square root of 2, transmissibility again becomes 1. Meaning that if you have a damping in your system, think about the car chassis. If you have damping in system and you set up the damping in a way the damping ratio becomes the square root of 2, it doesn't matter what the input frequency is. Right? Or let me rephrase that. Sorry, that was not the best way of saying it. Let's put it this way. If we have a system that the excitation frequency and the natural frequency, the ratio between them is the square root of 2, right? You have some natural frequency, K and M, knowing mass and stiffness, you have natural frequency. And you have the input frequency of the system. Now, if the ratio between the base frequency of the base and frequency of the natural frequency is the square root of 2, you are going to be exactly right here. Now, what happens here? At this point, no matter what you do, if you increase the damping of your system, decrease it, doesn't matter. The transmissibility is always 1. Meaning that if I had this system and this is oscillating, right? Should be able to do that. Okay. If it's oscillating, but the excitation is the frequency of the input, base excitation, and the natural frequency, the ratio between them, the square root of 2, doesn't matter how much damping I add to this system, I can't decrease the motion of the mass for some given input. The ratio is always 1. It's like as if there is no damping or as if there is no oscillation. They oscillate together. They go back and forth together. Now, the square root of 2 is an important point. Before this, if R is smaller than a square root of 2, frequency ratio, we are in this region. Now, what happens in this region? Pay attention. If I decrease zeta in this region, going from the red one to green one to yellow one to blue one, right? I'm decreasing zeta, meaning I'm lowering the amount of damping. TD, or transmissibility, increases, right? For any given R, doesn't matter where we are, if you're here at some specific point, let's say here, if I decrease damping, which means decreasing damping ratio, TD goes up, TD increases. What happens when TD increases? It means for any given input motion, the motion of the X increases. So if you're designing a specific damper or shock absorber, and if your frequency ratio is less than a square root of 2, what you have to do is you have to increase the damping to reduce the amount of motion transmitted to your mass. Now, if you look at the other side, this region, if your frequency ratio is greater than a square root of 2, and you're designing a shock absorber, what you have to do is the opposite. See, it's not very intuitive, because when your frequency ratio is greater than square root of 2, if you want to reduce, look what happens here. Pay attention to the plot. For a given frequency ratio, if I increase the damping, go from here to here to here to here, it goes this way. I'm going to have a smaller TD. Sorry. If I decrease the damping, I'm going to have a smaller transmissibility. So see how weird is that? If your frequency ratio is greater than square root of 2, in order to reduce the transmitted displacement from the base to your mass, you actually have to reduce the damping. It's not very intuitive, because before we knew from before that we always increase the damping to damp the motion. But that's not the case for basic excitation when the frequency ratio is greater than square root of 2. So let me summarize these points. Those are very important points when you're designing. So the first one was, let me phrase it in a good way, was the value of transmissibility is equal to 1, let's say, TD is equal, let's put this, let me finish the sentence. At R equals to 1, meaning that TD is 1 at R, sorry, at R equals to 0, right? We said at the beginning of the motion, when there is no oscillation. That's what we're talking about at this point. All right. The second one, the second observation, was that for an undamped system, when there is no damping at all, TD goes to infinity, like resonance, when R is equal to 1. And this is resonance. Third observation would be, well, let's put it this way. At R is equal to square root of 2 TD, transmissibility, displacement transmissibility, is 1 for all values of zeta. No matter how you change the damping, transmissibility is 1. Right? The motion between base and the mass is the same. Fourth one, I'm going to do it like this. For R smaller than the square root of 2, smaller zeta or lower zeta, value of zeta means lower damping, results in larger TD, displacement transmissibility. Remember, we're on the left side of the square root of 2. If I decrease the damping, TD goes up, meaning that we're going to have more motion in our mass for a given motion in the base. Now for R greater than the square root of 2, that was the weird part, that for smaller zeta, we have smaller TD, the right side. Oops, wrong direction, the right side. Again, very important when you design something. So you can't just increase the damping with this hope that, oh, every time I increase the damping, definitely I'm going to get less vibration in my system due to some base, if I have some base input excitation. The last one that I'm just going to put it here is, obviously we are interested to know where is the maximum transmissibility, right, in this plot. You saw it when I was talking about force vibration. As I said over there, the maximum now, it does not happen at resonance. If you look at the maximum points, if you connect these are where the maximums happen. Obviously, the closer we get to a non-undamped system, the closer we get to resonance. But where does this maximum happen? That's also something we're interested in. We want to know what is the most severe displacement due to some given, due to some input base excitation. That you can find, I'm not going to show how to do that, but displacement transmissibility is maximum. Let's also, we have to say not just as maximum. Maximum, oh, let's say this, maximum at Rm, which is smaller than 1. Obviously, it's not happening at resonance. R equals to 1 is resonance, right? Rm, some R which is smaller than 1. R at which the displacement transmissibility is maximum is 1 over 2 zeta, ready for that, square root of 1 minus 8 zeta squared minus 1. And that's where the maximum transmissibility happens. Write it this way, where, or let's put it this way, even better. Frequency ratio at which the max displacement transmissibility occurs. It's also important, we need to know that. All right, last thing I want to mention that I won't go to details about that. One more thing that we are interested in, well, we found displacement transmissibility, meaning that how the motion changes in the mass, or how does x change, or the motion changes in the mass when the motion in the base changes? Or how does that motion transmit from the base to the mass, if you want to look at this? There is another thing called force transmissibility. In this motion, obviously, when we move the base, right, the mass changes. The motion of the mass change. Right? Now, when I do this, due to this some motion, obviously, I'm also applying some force. When I'm moving this up and down, due to this motion, some force is applied from this mass, from this spring to the mass. Now it's important because if the motion, the way I'm moving the base, is applying too much force, or the force transmitted from this imposed displacement to the mass is too much, whatever structure I'm dealing with might break. Right? I have to make sure that the structure can actually handle that much force. So put this under force transmissibility. Force transmissibility. Just something to know. Summation of forces, if you go back to that free body diagram I draw, now I can write it in a little different. I can keep the force just on the left side and look at what are the components. So going back where the free body diagram was here. Instead of putting mx double dot on the one side, I'm just looking at the force components. Right? It's just what is the summation of forces. And for that, I'm just looking at the left equation on the left, or the free body diagram, sorry. So if I just write those down here, that'll be, let's say, summation of forces would be obviously minus c x dot, you can write it better, c, minus c x dot minus y dot, right, minus k x minus y. Right? This is pretty much what I get. Now keep in mind that my yt was y sine omega bt as the input, and my xt was x, I could say cosine omega bt minus theta. Right? Some harmonic output. Since the input is harmonic, the general form of the solution, and this is xpt, obviously, particular form of the solution, part of the solution. Now, if you plug this in, take derivative with respect to x once, find x dot, derivative with respect to y once, find y dot. If you plug this in, you can actually find ft. So I'll write it just for you right here. ft becomes m omega b squared y, well, omega b squared omega ny, square root of omega n squared plus 2 zeta omega b squared divided by omega n squared minus omega b squared plus 2 zeta omega n omega b squared, and would be cosine omega b t. Let me write it in a better way. Cosine omega bt minus theta 1 minus theta 2. We know theta 1 and theta 2 from before. But so this would be the force, I would say the force applied to the system. Right? It's not force transmissibility. Just pay attention. This is the force applied to the mass due to the base excitation or the base motion. Now, force transmissibility would be the magnitude of transmitted force. How do we find that? Well, I skipped the details, but you can find F. You can write Ft as some kind of harmonic force. And if I define this, let's put it this way. This whole thing as Ft. Right? Let's say this is Ft, the transmitted force from the input motion to the mass. Right? I can rewrite this as the form of transmissibility function, Ft over Ky, and Ky being the, you can think about that as the force, well, we can think about this fraction or this Ft over Ky as the magnitude of transmitted force. The motion you have in the base, how much force you're gonna have, how much force is applied to your mass. And again, when you're designing is important because that would be r squared over 1 plus 2 zeta r squared divided by 1 minus r squared plus 2 zeta r squared. And this is the force transmissibility. When you're designing something, again, it's important to know how much force is applied to the structure. Going back to the example of the shock absorber in a car, right? It's not only important that you minimize the amount of motion in this car structure because of some imposed displacement from the road. It's also important to know how much force is applied to a structure because of this motion, right? Because if you know the force, you can find how much, if you want to do some analysis, you can find how much stress your structure is going through. You can make sure that the material you're choosing can handle that much structure. We can look into the idea of fatigue life, that can your structure actually handle that much fatigue if you have some, this is cyclic load, right? If, it goes as a harmonic system. It's like a harmonic force. So if you think about what you learned in machine design, right? The input of a cyclic a force like harmonic force, periodic force, I would say, if you have something like that. Even if the stress you get from this force is not reaching the ultimate strength or strength that is your structure might be in danger, still the fatigue can have some effect. Right? You might have a problem in your structure because of fatigue. So that's why we need to actually be able to find this force. So keep that in mind. That's why we're talking about this force. And this is the force transmitted from the input. I'll call this force transmissibility. Or the force transmitted to the structure, to the mass, due to the base motion. So you can get, actually, you know what, let me fix this. This whole thing is not Ft, so don't get confused. Obviously, Ft is a function of time, so the whole thing cannot be Ft. What is Ft is this part. If you want to see Ft in this, it's thing you can think about this as Ft. So the force applied to the mass would be Ft times some harmonic function, cosine omega bt minus theta 1 minus theta 2. All right. I'll go over a couple examples in next class, and we'll see how actually we can put these together in different situations given some specific problems or a case. But keep in mind that just as a recap, fast recap, that we talked about force transmissibility and displacement transmissibility. Everything we did, right? We went through this whole trouble to solve this equation of motion. We started from free body diagram. We derived the equation of motion. We used what we learned from before for the force vibration of a spring mass damper to solve that. And we said, well, this is the steady state response. But what is more important is how much, if you want to design something, how do different parameters change? I told you before, graphs are very helpful when we are designing something. As you see here, we figured out, we had a couple of good observations based on the transmissibility, displacement transmissibility, which can help us exactly how to tweak different parameters when we're designing a specific system, right? Under base excitation. And eventually, I just told you about force transmissibility. And as I said, it's important because you also have to take into account that you don't want to just reduce the amount of motion in the structure mass. Well, most cases, there are cases you want to increase the amount of motion, which is when you're harvesting energy from vibration. What's this different story? But generally speaking, you want to suppress the motion when we have vibration, when you're designing engineering systems. You need to also know the force transmitted. So we can also take into account that you don't have a huge amount of force that your structure cannot handle depending on the type of material you are choosing for your design.